Today we will see the losses in the case of a synchronous machine in general. We can divide the losses into the constant losses and variable loss. And we have four different types of losses, that is electrical, copper or ohmic losses, then iron losses, what is also named as core loss or magnetic loss. Since the machines are rotating or moving parts, we have the mechanical loss as a third type, and we have stray load loss too. First of all, we will discuss the electrical losses, that is the copper loss. In the case of electrical losses, we will have to consider the field copper loss, armature copper loss, as well as the electrical losses that can happen between the brushes and slip ring in the case of synchronous machine. If we consider the excitation voltage to be constant and the power factor to be constant, then the field copper loss is constant and is given as VF-IF or IF square RF, where VF is the supply voltage to the field winding and IF is the current that is passing through the field winding, and RF is the resistance of the field winding or field circuit. Armature copper loss is a variable loss. It depends on the load current and is given as 3I squared Ra, where I is the current that is passing through the armature winding per phase armature current and Ra is the per phase resistance of the armature winding. And we have the loss that can happen between the slip ring and brush arrangement because of the supply that is given through slip ring and brush arrangement to the rotor side, and it can be neglected. The second type of losses is magnetic loss or core loss, or it is also called iron loss. We have two different types of iron losses, that is hysteresis loss and eddy current loss. And the losses happens because of the reversal in magnetism. And we know how it can be reduced, that is eddy current can be reduced by reducing the thickness of the laminations, and hysteresis loss can be reduced by going for silicon steel. And these losses can be considered to be constant provided the excitation and the PF is maintained as constant. So the magnetic losses can be considered to be constant loss. Next we have the mechanical loss. We have two types of mechanical loss, that is frictional loss and windage loss. Frictional loss is due to the friction between two solid parts. We have the bearing and brushes where these frictional losses will be occurring. And second, the windage loss is because of the friction between any solid part and the air, or we can consider to be having more of ventilation loss. And these two losses, that is the mechanical losses, can be considered to be constant if we consider the speed of the machine is constant. The fourth type of loss that occurs in synchronous machines is stray load loss. It is same as that of the core loss that we had already. We have the core loss that occurs due to the armature leakage flux and armature reaction. Here this loss occurs in the iron surroundings of the windings. and the loss depends on the load current. So we will have to consider the stray load loss as a variable loss. So to summarize regarding the losses that occur in synchronous machine, we have constant losses and variable losses. Under constant loss, we have field copper loss, magnetic loss, and mechanical loss. When we consider these losses to be constant, in the case of field copper loss, we consider the excitation voltage and power factor to be constant. For magnetic loss also, to make it as constant, the conditions are the excitation to be constant and power factor to be constant. In mechanical losses, if we need to consider as constant loss, we will have to consider the speed of the machine to be constant. And under variable losses, we have armature copper loss and stray load loss. These are variable losses because it depends on the load current. We will see the efficiency of an alternator or synchronous machine. It is given as eta equal to output divided by output plus loss, or it is output divided by input. We have direct method as well as indirect method to measure the efficiency of a machine. In direct method, the machine will be actually loaded, and in the case of alternators or synchronous machines, since it is of huge capacity, if we go for direct method, it will be resulting in power loss. So preferably, in order to measure the losses or to obtain the efficiency of a machine, we will have to select indirect method. Here in alternator, the indirect method will be requiring a calibrated DC motor. Calibrated DC motor implies there is a motor for which we have already determined the losses for varying load conditions or operating conditions. We will see the indirect method by which we calculate the losses in the machine and thereby the efficiency of the synchronous machine. Here as the first step, the alternator is driven at synchronous speed by using the DC motor, and it is the calibrated DC motor that is used. So when the alternator is run without excitation at synchronous speed, the input to the alternator is the output of DC motor, and that is the mechanical input that is given. And since there is no output from the synchronous generator or alternator, whatever be the input that is given to the synchronous machine can be considered as the mechanical loss. So the output of DC motor will be equal to the mechanical losses that occurs in alternator. In second case, the alternator is driven at synchronous speed and the excitation also is given to the synchronous machine. And it is driven by the DC motor itself. So whatever be the output of DC machine or the input that is given to the alternator will be just used for the losses, that is the magnetic loss and the mechanical loss. Since we have already calculated the mechanical loss in the first step, we can separate the magnetic loss that is given as the total input that is given in step 2 minus the total input that is given in step 1 will be giving the magnetic loss, or in step 2 whatever be the input will be a combination of mechanical laws and magnetic laws. In third step, the synchronous machine, that is the alternator, is run by DC motor at synchronous speed, and along with the excitation for synchronous machine is also given. Alternator armature terminals are short circuited and the field current is adjusted in order to circulate the rated armature current. The input to the alternator, that is the output of DC machine, will be the sum of armature copper loss, stray load loss and mechanical losses. Here we are circulating the rated current through the armature terminals, that is why we will have to consider the armature copper loss. And because of the current that is passing through the field circuit and through the armature conductors, we will have to consider the stray load loss too. And the mechanical losses is to be considered because it is run at synchronous speed. And the magnetic loss in this case is neglected just because the terminals are short circuited and the excitation current required to circulate the rated current will be less. So we can have the equation stray load loss is equal to the total power input that is given in step 3 minus the mechanical loss minus the armature copper loss. The armature copper loss should be found out. The fourth step, field and armature resistance are to be measured by voltage and current method, V by I equal to R. And from that we can find out what will be the field copper loss as IF square RF and the armature copper loss as 3I squared RA, where I is a full load current, and if the efficiency is to be calculated for any other percentage of full load current, you can go for X times I. So now by indirect method, we have separated the mechanical losses, the magnetic losses, stray load loss, and the armature copper loss and field copper loss can be calculated too. The advantage in the case of indirect method is the power required for measuring the loss will be very less, and there is no requirement of electrical loading. If an alternator is to be loaded in direct method, we'll have to have the equivalent loads or large amount of loads depending on the rating of the alternator, and the accuracy will be far better in case of indirect method. And even if there is any inaccuracy that can happen, it will be very small because we have considered the losses separately, and the portion of the loss that can or the inaccuracy that can creep into will be very small. So today in this lecture we are discussing different types of losses that can happen in the case of an alternator and how these losses can be measured by indirect method. Hope you have enjoyed and understood the portions. Thank you.